Okay, hello. Welcome to week 1 of the intro course. It's nice to see everyone here. Yeah, let's just get started because we're 5 minutes off as usual. I'm going to start with groups. So raise your hand if you're in the Discord server and in a group. Okay, I should have done it the other way. Raise your hand if you're not in the Discord and not in the group. Yeah, okay. Just you, no one else. Okay. Maybe ask someone around you, or are you not in a group either? Oh yeah, you can help them. Yeah, okay. Looks like we're all good. Okay, now I just want to see if it's balanced. So raise your hand if you're in group panda. Okay, like we're gonna need some more pandas. All right, dog. Okay, orangutan. Okay, dolphin. Okay, raccoon. Okay, and hedgehog. Okay, that's not too bad. Can you join panda? Or if you can't figure it out. Huh?
I just choose
You just,
it. I just choose it.
you just chose it? Okay, perfect. Yeah, okay. We might need to rebalance, but should be good. Again, that's your TA. That's the place to ask questions. If I move you later, and you really like your other TA, just DM them or like ask them in the general chat. Or just ask your new TA. Should be fine. But on to the meat of today. There's the attendance QR code. Please fill this out. This will be up till the end of the hour, but this QR code won't. And again, attendance is tracked from now on. And as a reminder, you need to come to 7 out of the following 9 meetings if you want the certificate by the end. We'll give everyone a second for that. The link is also at the bottom. This is also in the resources chat in the Discord. I think it's the one with the turtle emoji. Yeah, it is. So if this goes down, they start their thing and you don't know where to find it, it's in the Discord. And this week, hopefully most of you got that, I will be switching the screen. Again, it's in the Discord. This week, though, will be Unit 1 in the Mega Doc. Oh, that did not work. I want to open this. So it'll be a bit of reading, bit of some videos. So go through this, answer the synthesis questions over here. There's some more right here, like after watching some really short videos. And then there's this technical project and this non-technical project. The technical project, you'll open it up by clicking this. And again, I'm doing a quick overview. If you have questions when you actually get started, please just ask in the chat. And when you get to the collab though, click file and then save, copy, and drive. You can't edit this one, which is by design. We don't want you to. And this isn't easy. This is like you're already implementing. Like you can kind of see some of these imports, like NumPy, sklearn, and I think there's PyTorch. If not in this one, it'll be by the next one. So please ask questions if you run into any. Again, this stuff we know is not easy. But back to this. Yeah, there's also a non-technical project. If you dislike Python, I don't know why you would, or if you judge that don't have experience, you can do this. Just read through it, fill it out, and submit it. And then the submission is also linked in the Discord, but it's this form that looks like this. You'll just upload your project and synthesis question separately, put it in like a PDF or a Word doc, whatever works. If you have issues with that, again, the chat for everything. And then on Tuesday, we ask that you submit 1 synthesis question. The reason for this was because the first time we ran the course, everyone started it like Thursday night or Friday night, and like Friday, and then it was due Friday night. So no one like got it done on time. So by doing this, we hope you'll do 1 synthesis question and then be like, hey, why not just start on it? And you get started early. So yeah, and this will just be like, just send it in the chat, the one with the brain. And yeah, hopefully that should get some conversation going as well. Any questions on all that? That was a decent bit. And again, if questions come up in the future, in the following week, go ahead and ask it in the chat. And ask your TAs. Okay, cool. Then I will pass it on to Jeffrey and Shay for our lecture.
Okay, hello everyone. Welcome to I2's first unit of the course, the Neuro AI course. And today we'll be going over machine learning, kind of like the basics. My name is Jeffrey, and we also have...
Hi everyone, I'm Shay.
And we're a T's for this course. So hopefully you all did like this week's reading, week 0. It does go over some basics, such as like matrix algebra, which will be mentioned here and there. And despite that, I've attempted to make most of this presentation like intuitive and basic. And Shay will be going more into like the complex mathematic stuff. Just out of curiosity, how many of you are freshmen? Yeah, okay, that's cool. And how about not freshmen? Okay, interesting. So before I start, I thought I'd like to share this quote. I'm like a quote person. Hopefully some of you are like quote people. So the limits of my language are the limits of my world. So I find this quote to be kind of like cool and stuff and somewhat correlated to like AI. And hopefully some of you like take this with you. So what exactly is machine learning? So fundamentally, it's having machines understand semantic things through having it recognize different patterns. So it's kind of like applied stats. So in stats, we have humans analyze like data sets and find meaning in it. Whereas in machine learning, we try to get like the machines to understand what this data means semantically. And we'll be using this 3-step process. We'll first procure some data, and then we'll choose a model, and then we'll create or use an optimization algorithm. And we'll go more into optimization algorithms in the next unit, which is about deep learning, I think. And usually it's not just these 3 steps, it's more complicated, but we'll just be using these 3 steps for simplicity. And one thing to do note about machine learning is that your model is only going to learn what you give it, so the quality of your data set matters a lot. And here's kind of like a little diagram to explain how everything like connects to each other. So machine learning is just a small part of AI, and deep learning is another smaller part within machine learning. Okay, so let's start off with a very basic question, hopefully. So what is the difference between a horse and a chair? If anyone's willing to tell me one difference. Because they're both brown, you can sit on both of them, and they have 4 legs. What's one difference between horses and chairs? Hopefully you're not like AI too, so. Oh yeah. Yeah, that is a splendid answer. So one of the differences is that horses are kind of like living things and have like anatomical structures and stuff, whereas chairs, they don't really like have that. So for us humans, it's easy to understand like this is a horse and that's a chair, but for machines, it's like a different thing because they don't have brains as cool as ours. Oh. So our goal is to have a machine distinguish if a picture we give it is either a horse or a chair. So I created this little machine here. It's called the Machine Learning Binary Object Transformer. It's not like an actual thing. It's like completely fictional. And we'll just call it our ML bot. So we should be able to feed pictures of horses, and it's going to tell us it's a horse. And if we give a picture of a chair, it's going to know that it's going to be a chair. So the first thing we could do is we could make some data out of this. So we will label our columns as different characteristics or variables that help distinguish chairs and horses. So horses tend to have eyes and aren't usually made out of wood, and chairs are usually made out of wood and don't necessarily have eyes. And we could also have things or data, or in this context, we're going to be using pictures that will be our samples that will feed our machines. And we're just going to simplify it a bit more. We're going to turn yeses into ones, and we're going to represent no's as zeros. So it's beginning to look a lot like matrix algebra. So how does our ML bot actually determine if a thing is a horse or a chair? So let's feed it our data. So for our visualization, we can plot our data as 2 points on a graph. So let's label the x-axis as does it have eyes, and the y-axis as is it made out of wood. So now that we've plotted our things, we can draw a line to separate horses and chairs. And this is referred to as support vector machines. And at a very low level, it's like this little line or plane that separates or helps classify different things. You'll learn more about it in like your reading. So on this side of line, we have chairs, or things that appear to be more chair-like because we have the variable, is it made out of wood? So the higher the value it's made out of wood, the more likely it is to be a chair. And the same goes for horses. So the more likely or higher value we assign it to having eyes, the more likely it is to be a horse. And this is like a grossly simplified version of what this actually does. You'll learn more complex stuff later. So I'll pass it on to Che to talk more about support vector machines.
Okay, so now I'm going to cover the basics of support vector machine. So first of all, what is a hyperplane? So a hyperplane is a subspace of one dimension less than the dimension of the full space. So in this picture, I have x1 and x2, so that is 2 dimension. And so our hyperplane would just be 1 dimension. That's why it's just a line here. So for another example, if I have a 3-dimensional space, can anyone tell me what would be the dimension of the hyperplane in 3D? Yeah. Yeah, that would be 2-dimensional. So a hyperplane in 3D would be a plane instead of a line here. Okay, so now we have 2 groups of data, and we're trying to find a hyperplane that best classify those 2 groups of data. So this dashed line here is called the negative hyperplane, which just touches the point of the negative class. And this dashed line here is called the positive hyperplane. So that just, the hyperplane touches the points of the positive class. And specifically those 2 points that are closest to the hyperplane are called the support vectors. Those are the points that will help you to define like the best hyperplane. And the distance between these 2 dashed lines here is called the margin. And basically, we're trying to find the hyperplane that provides us with the maximum margin here. So that's the one that have the best classification performance. So that's the basics of support vector machine. Does anyone have any questions? Yeah, so those are just terms related to support vector machine. So basically, it's like if you have 2 groups of data, and you can have multiple lines that successfully classify those 2 groups of data. But here we're only looking for the best one that can successfully like classify those 2 groups of data, and that would be the one that has the maximum distance from both of the classes. Is it good? Yeah.
Is it kind of like a line of best fit?
It's not like a best fit. You're not drawing a line, like you're not connecting the points. It's just you're trying to like differentiate between those 2 classes and draw like a margin. Yeah.
What does maximum mean?
Like so if you have these 3 different separators, like technically you can have like different distance between. So for example, this is my hyperplane, and this can be the positive one, and this can be the negative one, and there will be a distance between these 2 hyperplanes, right? So there will also be a distance between here, and also a distance here. So basically, you're trying to find the hyperplane that has the maximum distance, and that would be your best hyperplane. Does that make sense?
Equally far apart.
What?
Equally far apart from positive data.
No, like you're trying to find the maximum distance. The one that has the maximum difference between the positive hyperplanes and negative hyperplanes.
Or to kind of like explain it more, so pretend like the blue, hopefully none of you are like colorblind, but like hopefully the blue is like going to be like horses and the green is like chairs. We want the line to be as far away from the data so that we don't incorrectly classify it as like the other thing. And so that's going to be like the SVM. There's going to be like 2 videos in your reading, I think, that go over it.
Yeah, but just keep in mind for now that you're just looking for the hyperplane that has the maximum margin from both of the classes, and you'll know more details from the videos and reading materials. Yeah. Any more questions? Okay.
Okay, so let's just return to our machine learning bot. And so let's see how good our model actually is. So we're going to feed it this picture of a chair to us with some googly eyes and see what machine learning bot thinks of this. So for MLBot, it incorrectly classifies it as a horse because it has eyes. So from the data, we can see that it has eyes and it isn't necessarily entirely made out of wood. So it would incorrectly classify it as a horse. So, oops, spoiler alert. What are some things we could do to like make it better at classifying different things. Yeah, so one of the things we could do is add more labels. So we're going to add more like features and variables to help distinguish like chairs and horses. So this way we can, by adding more characteristics, we're telling our machine that there are more things to just like that make a horse and a chair. Oh. And we could also just add more data. So we're just giving more samples to our MLBot, so it has a wider understanding of like what are the different characteristics of like horses and chairs. Because not all horses are going to be brown, and not all chairs are going to be made out of wood. So we're just going to add like more data and more variables. So here's like a little visualization on what I mean by like adding more samples. So we don't want to just give it like two things that are just like the same. We want to have like variance in our data to make sure like our bot could classify like different types of horses and different types of chairs. Otherwise, it's just gonna like incorrectly classify like this chair as a horse. So in essence, you want to create models using a wide variety of like data, and you want to include like edge cases or potential like exceptions that might like bypass your algorithm. You want to give good data or quality data to your bot, and it will give good stuff back. And if you just give it like biased or some bad data, then it's not going to look good for you. And we're just going to go over a few of the optimization or not optimization modeling stuff.
Okay, so so Jeffrey was talking about how to use different features to classify different objects. And so what if the data set is just too big and you just want to reduce the dimension of the data? So that's when we're going to use the principal component analysis. So this is, so for example, in the videos that will be given to you along with the reading materials for this week, there will be an example where you have to determine like which country is the happiest country in the world based on several features provided, such as GDP, life expectancy, social, and what else? Freedom and corruption, etc. So you can have like multiple, like hundreds of features that you're going to use, but by using principal component analysis, you're only going to extract like several most important components that we're going to use. We're not going to use all of them. So basically, PCA just takes in it actually takes in like all the features you have, but by running the algorithm, it will return you with the several most important components. You will just use those several components. But it takes all the features or all the components, but it will generate the most important components for you. Does that make sense? Yeah.
So will it combine components into one thing, or?
Yeah. It's kind of like taking all those original components and then generate new components for you at the end. Yeah. So yeah, as you can see so we just randomly picked 3 factors here: GDP, social, and life expectancy. So each of them have their own direction. So basically, PCA just looks for the direction along which the data varies the most. So how do you actually know like which component matters the most, or like how do you determine the principal components? You can do this by just see like which direction gives you like which direction make the data vary the most. So you can do this by so if you like select a random or like so any component here as this horizontal line, and these x's are your data points. So in this example, it will be your countries. So you just project each of the data points onto those components, and then you see the dashed line here. That's how you can see the variation of the data points. So basically, you're just looking for the components that makes the data vary the most, like that has the most variation along the component. Anyone has any question at this point? Oh yeah.
So essentially, like you think of that as like a linear transformation where you like project the vectors, and then I think the slide is something about like eigenvalues. So like whichever has the highest lambda or eigenvalue determines like whichever one like varies the most. Is that how this algorithm works?
Yeah, we will be introduced this later, but this is the main idea, or like the geographic motivation behind this. So we're
Sorry, I think you are right though. It is in projection. It's an exact projection of the data point onto the future to figure out. But like, yeah, you'll get into the math, right?
Yeah, I'll get into this later.
Confusing, so please do ask questions. These are great questions.
Yeah, so basically you're just trying to see which component has the most variation of the data. That's the main idea here. And so we're clear now that we're just trying to find the component that maximize the variation, right? So we'll have a formula that measure the variation of the data. And basically we're just trying to maximize that equation. And then eventually you'll get into this step. This equation is like C times U equals lambda times U. And the C here is just a matrix, and the U here are the principal components that you generated from PCA. And the lambda here is, it tells you like how important is the generated components. So as she just mentioned, these are called, the U are called the eigenvectors, and this is called the eigenvalues. So it's okay if you haven't heard about those terms before, but just keep in mind that those just represent the principal components that's being generated, and this is the value that tell you how important the component is. So usually it's like the larger the value, the more important the eigenvector. So say that my GDP has a lambda value 4, and my social has a lambda value of 3. So that just means GDP is a more important component than social. Does that make sense? Okay, good. Yeah, so basically from one question, you can have multiple generated principal components. So that means you can have multiple U's, and each of them have corresponding lambda value. So that just means from every question, you can have one or multiple principal components, and you will also get their associated importance value. So that's the main point here. And now I'm going to introduce a concept called singular value decomposition. So this is a technique that you could use to perform the principal component analysis. So for the more detailed relationship between these two, it's a little bit more complicated. But if you're interested, you can reach out to me after class. So the singular value decomposition is like given a matrix M, and then you can just decompose this M into 3 different matrices. It's called U, sigma, and V transpose. So the geometric motivation behind it is like, so you start off from a unit circle, and then that's the formula of unit circle. Does everyone recognize it? And then if you apply a transformation matrix A onto those 2 vectors on this unit circle, you'll get another vector X and Y. I don't know how to say that. But yeah, basically after you apply the transformation matrix, the vectors on that unit circle is being stretched or scaled so that you get something different. So finally you will get the ellipse here. So that's this SVD do something similar, because if you decompose the M into U, sigma, and V transpose, so you can just think V transpose as a rotation of the vector, and you can think of sigma as a stretching or scaling of the vector, and you can think of U as a final rotation. So eventually, you will just go from a circle to an ellipse. That's just the geometric motivation behind SVD. Yeah, does anyone have any questions? So this concept is not that important, but it's just a motivation that I would like to introduce to you guys. So yeah, as I mentioned before, if we have an input matrix M, so M times N just means it has M rows and N columns. And you can basically just decompose it into 3 different matrices. So it's called U, sigma, and V transpose. So okay, I'm gonna introduce some important terms there. So transpose. So how do you get a transpose of a matrix? So for example, if I have A, B, C, D as my original matrix, then the transpose of it can be denoted as a small t here. And then the transpose of it would just be this. So you basically just interchange the rows into columns and the columns into rows. That's how you get the transpose of a matrix. And diagonal matrix is like you can only have the non-zero entries along its diagonal, and everything else should be zero. So like this is a diagonal matrix, like this, and this is also a diagonal matrix because both of them, they only have the non-zeros along its diagonal. As long as you make sure that everything else is zero, it's a diagonal matrix. And yeah, does anyone have any question about the concept of matrix? I think that should be straightforward, right?
If you do have questions, because you haven't done linear algebra, you can ask the chat.
Yeah, those are. Any questions?
But you shouldn't need to know too much of it. This is just like a method. You'll see in the videos explain it in a different way as well. That like animations.
Yeah, like don't worry too much about those terms. It's just something that I would just briefly mention when I talk about the SVT. So last two terms, the identity matrix is a special form of diagonal matrix, but it just has all ones on its diagonal, and everything else should still remain zero. It's just like every entry on the diagonal should be ones. And orthogonal matrix is just, so if this is my matrix, this is the transpose of matrix. If you multiply them together, you should get an identity matrix. So that's the definition of orthogonal matrix. So like, yeah, those are just like the definition of the matrices. So yeah, basically you get those three separate matrices where U and V transpose are called the orthogonal matrix, and the one in the middle, the sigma, is an diagonal matrix where you see like it has all the color on its diagonal. So that means the singular values are all on the diagonal of the matrix, where everything else should be zeros. So how do you find the singular values? You just look at the sigma matrix and you just extract the value on its diagonal, because those are the only entries that have some numbers, right? Because everything else is just zeros. So that's how you can find the singular values. Okay. Yeah. So so we will not go over how you actually get those three matrices, but if you know that something called MATLAB is a numeric computing tool, then you can just input this. You can input your matrix M, and you also input this command. So it will just automatically return you with those three matrices. So that's how you get those three matrices by using the computer. So that's a simpler way. So yeah, let's look at an example. So this is our input matrix M, and so we have three matrices in total, right? So this is the first matrix, that is the third matrix, and the one in the middle is our sigma matrix. So that is so as I just mentioned, this is a diagonal matrix, and all the singular values are on its diagonal, right? Because every other entries are zeros. You can only find something that is non-zero on its diagonal, and those entries are just the singular values. So so the singular values tell you the importance of the corresponding vectors. So for example, the 4.6 is like bigger than 2.6. So that just tells you like the vector that's corresponded to the 4.6 is more important than the vector associated with 2.6. Does that make sense? Yeah, anyone please ask questions if you don't really understand like how this works. Yeah, so basically it's just the singular values tell you the importance of its corresponding vectors. Yeah.
When you talk about the diagonal matrix, shouldn't that be a square matrix?
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6.
Neuro's previous slide shows, I think the previous slide, like sigma is n by n. So it matches the column. There's a value for each column. So it tells you the importance of each, like each feature in this case is a column in the original matrix n. That makes sense.
Like the sigma matrix is not a square matrix.
But then a diagonal matrix has to be a square matrix. Right?
Does that have to be?
That I don't know about the technicalities, but in this case, it's not.
Yeah,
Like the diagonal is when like the row index and the column index, when they're equal, that's diagonal. So even if it's shortened, it's or squished with wise, as long as like, where I equals j, you kind of think about it like that. It's the same, and that's diagonal.
yeah, we could be wrong. We'll check that out like after class.
Like it might not technically be like a true diagonal matrix then, but it is. It has values on the diagonal. Sigma, like, yeah.
Yeah, so the main idea is that the diagonal matrix has singular values, and the singular values just tell you the importance of the vectors.
We got it.
Oh,
Yeah, so if I'm not to go like too into the math, but like for the sigma matrix,
mm-hmm.
would the values on the diagonal, the significance values, are those like eigenvalues? Or like
I believe that there's a difference between eigenvalues and singular values, right? You have to compute one first, and then you get another.
singular values on the diagonal would correspond to the eigenvalues?
Now they.
I
don't
don't
really
think so.
remember, actually. I would. If you're interested, call me and see me after class, and we can check with some of the others too, or
Mm-hmm.
Just like the
that they. If you're interested, it definitely can. And again, if it doesn't answer it, just come ask us, and then we can definitely find the resources and answer those questions.
Yeah.
Where is SVD used in the classification algorithm?
So SVD is something that, so you remember the PCA, right?
Yeah.
So this is a technique that could be used when you are doing PCA.
Sigma the matrix that's used for that, and then you look at the.
Yeah, that's a good question. Like, I have a like short proof or like a really good explanation that answers your question, like the relationship between SVD and PCA. So you can reach out to me after class and we'll talk about it. Yeah, next slide. Next slide. So yeah, so this is called lower rank approximation. This is an application of SVD. So as I previously mentioned, you have your input matrix, which is n by n, right? And then you decompose it into 3 different matrices. And the k here is the number of singular values that you choose to keep. So for example, so you can choose different k values. You can say that k equals 1, k equals 5, k equals 100. But depends on the number that you choose, you'll have, so basically it's like you want to reconstruct your original matrix, but just use those matrices with the reduced dimension. Like, so for example, in your original matrix, you have these 3 after decomposing. And if you choose, so you remember that those are the singular values along this diagonal. So say that I have 5 singular values on this diagonal. And if I choose, so that means k equals 5, right? And if I choose k equals 3, that means I'm going to reduce the dimension of each of the matrices here by some size. So it's basically an idea of reconstructing the original matrix, or like reconstructing the approximation of the original matrix, but just use less data. Okay, that's the main idea here. Anyone has any question? Yeah.
doesn't reducing dimensions like defeat the purpose of originally like adding more data to our data set that's being processed? Like even though we have the same dimension for a matrix at the end, we're using.
Yeah. So notice that. Yeah. Yeah. Oh, sorry. What was the question again?
Yeah. So like, doesn't reducing the dimension or like getting rid of some of the data, like doesn't that defeat the purpose of adding that data in the first place?
Mm,
I don't think we're necessarily just like removing data. We're more like kind of like decomposing it and just like making it more simple to understand.
so like k is the number of singular values, like, right? Like the singular values, it tells you how important that corresponding eigenvector is, right? So like basically, if like even if you reduce the number of singular values that you choose to keep, that is it's still, because after the computation, it still keeps the most important information that you want.
Okay, so you're keeping like the values that are like the highest or like most significant.
Yeah.
And reduce the dimensions from R to K.
Yeah, so it's like in the sigma matrix, the singular value is usually ordered in decreasing order, right? Like from the top to like decreasing order. Yeah, I think that's the case. And then so you're only like reduce the size of the matrix by this, so you're still keeping like the important information. And we'll introduce an application of this, and you will get better understanding. Yeah, next time. Yeah, so this is a really interesting application of lower rank approximation. So say that you have this picture, but you want to save some storage space. So you want to compress the image a little bit. So you can do this by using the SVD. So so these are 4 different images that's being reconstructed using SVD. So as you can see the difference between these two, this one is really blurry and this one is kind of clear, right? So because this one we choose the k value to be 1, that's called rank 1 approximation. And this one we choose k to be 10. And this one k is equal to like 50 and this one k equals 100. So like basically as you can see, the larger the k value, like the better the quality of the image. So like when you choose, so could you go to the previous slide? So basically, like this is the number. This is the k value, and the 4 pictures that we're trying to regenerate, they have the different k values, which means you have different number of columns, or like singular values, retained, right? So like if you keep more information from this, or like the larger your k value is, like the quality of the picture is going to be better. So like if k, so say that k is equal to 5 here, and if I move the k to here, say like k equals 7, and then you're just using more data, so your picture would just be a better quality. Does that make sense? Okay, next slide. So yeah, this is the code that we use to generate the picture in MATLAB. So basically, you use the SVD algorithm to get your 3 different matrices, but you just choose different k values. It's the number of singular values that you choose to keep. And then so you get different quality pictures by using different k values. And the larger the k values, the better the quality of the picture. And this is completely optional. I think it's just an interesting application that I would like to introduce. Yeah. Yeah, next slide. Okay. Yeah, that's basically all we're going to talk about, like all the important things that we're going to talk about today.
Yeah, so these are like key terms that I think you should take away the most because they're going to be in the reading. You don't have to know like everything, so I'm just going to give you all like 10 tips for the course since we were also previous students of this course. So for my first tip, it would be to utilize your resources. Just ask questions whenever you get confused. You can ask the TAs, leads, us, the Discord, and even each other. So be sure to ask questions if you ever get stuck. And this was said before and when I took the course. So what you put into your learning is what you'll get out of this course. So be sure to, again, like ask questions if you don't really like understand anything, because a lot of this is going to be like pretty difficult to like understand. And you don't have to know like everything right off the bat. If you don't get it, you could just like move on. So when you go into the reading, you probably won't understand everything, but be sure to just like read over it, ask questions, and then like look over it again, and then you'll begin to like understand more of it. And here's like a general tip: 20% read equals 80% knowledge. And yeah, that's the end of our presentation.
Like, does anyone have any questions about the lecture? Like, you can ask anything.
if not, feel free to like come up and ask us like now when we're getting ready to leave. And if you had questions, like I think if you guys, so feel free to come up to us and we can talk more to them. But yeah, have a
Wait.
Oh, yeah.
I don't believe that. Somebody has a question.
Is it too fast or too difficult? Like, should we go over something simpler for the future presentation? Yeah.
So, if I'm understanding correctly, SVD is part of the principal component.
It's just a technique that you could use when performing PCA. And because both of you seems like to have the question about relationship between SVD and PCA, you can reach out to me after class, and I'll show you a proof.
Yeah, so you're saying it's just a technique, but there's other techniques you can use?
Yeah, there are definitely other techniques, but today, like in today's lecture, we're only introducing this one. Yeah.
Are we supposed to read any prerequisite, like reading the read before this movie?
No, yeah, you should show like the idea of this is to now when you see the reading, it'll be like a big. It's like I saw this dimension. Go back to the video because just reading it is. I mean, either way, like the first I guess thing that is gonna be it's a lot. It was a lot for me when I first took the course. So.
And then is PCA like classification algorithm, like structure classification,
Could you say that again?
this is principal component analysis, like one of the main algorithms used for classification.
Is that the main algorithm? I think this.
It's like one of the models, I think.
So, PCA is a dimensionality reduction technique. So, it's usually used before classification, and it's really prominent in something like bioinformatics. One of the reasons is because in bioinformatics you usually have a lot of data, and it's also many dimensions. So I actually used it. I don't know how many of you saw the talk I did. I don't even know if any of you know who I am. But when I went to Australia and worked on neurons and things, I used it to analyze the data because we had readings of voltages of neurons, and there were hundreds of thousands. Well, we didn't. Sorry, that's an exaggeration. There were hundreds of thousands of neurons. We didn't have hundreds of thousands of neuron readings because our electrodes sucked. But we had hundreds of thousands of time steps because it was sampling so frequently. So what you do is you use PCA to shrink it down into something that's way more manageable. And then, so that wasn't the classification case, but you could do that with something that's very high dimensionality, shrink it down into something, and then classify it, because it gets rid of a lot of noise and just really hones in on the signal.
So from understanding correctly, kind of there's to compress the data, and then there's to have like the most important things.
Yeah.
No leftover.
Yeah, and one of the reasons people really like PCA for dimensionality reduction is because you still retain, you can still visualize what the reduced form is. So it's kind of cool. I remember in my ML lectures they showed a bunch of faces, and then it was a huge data set of pictures of faces. I mean, I don't know if that's still in the slides. It used to be at some point.
Like what we would do learned it.
I don't know.
These averages all the time?
Yeah, so then when you reduce all of the faces into like 10 principal components, you can visualize those principal components, and it will look kind of like an average of a face. So it's kind of, and that's one of the reasons people really like PCA is because of visualization.